My name is Vladimir Chigrinov, and the title of my presentation is Photoalignment and Photopatterning Nano-size Azodye Layers for New Liquid Crystal Devices. I represent Hong Kong University of Science and Technology and Nanjing Jinsui Optical Technology Institute in China. Actually, I am a fellow of SID, and I am also got Zlotovaki Prize, and I am fellow of National Academy of Technology in China. And I have been 2 years in talent in China. I am the co-author. I'm author and co-author of 6 books. My Web of Site index is 42, and the Google Scholar index is 56. I have 38 United States patents, and the latest United States patents was filed last year. I have a lot of collaborators, not only in China and Hong Kong, but also in Russia, in Switzerland, Japan, Australia, Sweden, and other countries, and definitely China. So the topic of my presentation is photoalignment, new LCD display technology, and other things which I would like to tell you to become very important if you use photoalignment technology using Nanolayers. As for photoalignment technology, we have written a book which has been published in 2014, and now we are trying to revise most important materials which has been done for photoalignment technology are Azodye nanolayers. So this Azodye is rod-like molecules which has absorption oscillator parallel to the direction of the molecule. So the stable position of Azodye is perpendicular to the polarization of the light, because in this case there is no absorbance. We have published the model in Physical Review E in 2004. Azodyes can be used not only for liquid crystal alignment, but also for polarizers, retarders. So the idea is very simple. You have Azodye nanolayer with a thickness between 1 and 10 nanometers. You align them with polarized light, and finally you will have very high quality of alignment of these nanolayers. If you look at AFM picture of Azodye nanolayers, you can see this is very unique and very good. The resolution of Azodye nanolayers, which we can define by writing diffraction grating, is better than 100 nanometers. So on the level of our optical equipment, Azodye nanolayer can be used for photoalignment of liquid crystal, not only on glass, but also on plastic substrate, and the corresponding characteristics are very similar. If you like to stabilize Azodye alignment, you just put liquid crystal monomer, align Azodye, and then polymerize this monomer by photo or thermal polymerization. Then you will have very stable Azodye layer alignment. It has thermal stability, so after 24 hours at 100 degrees C, it will have same electro-optical response, and it will have photostability after 12 hours after illumination of 100 watts per centimeter square. So Azodye alignment can have a very good quality of liquid crystal films, and the table which shows the quality of liquid crystal films like anchoring energy, image sticking, and so on, in comparable with usual technology. You can also get a lot of other different pictures using Azodye nanolayers. You can make diffraction grating by two-step illumination by Azodye, and you can make Q plates which are used for instance, for optical data processing. And you can also control the light in fibers. You just put liquid crystal aligned with fibers, and you can have different elements to control light in the fibers. You can have filters, tunable wave plates, to enable gratings, polarimeters, and so on. So, roughly speaking, there is a lot of advantages of photoalignment technology. Eliminating of charges and impurities, very high quality of alignment like tilt angle and anchoring energy. And also you can foresee different applications, new applications of liquid crystal in holography, in curved and flexible substrates, and also in photonics. You can provide many different new elements, which I will tell you about them. If you look on this slide, you can see that Azodye photoalignment technology and photoalignment technology get much better quality of liquid crystal devices. This is a picture of TV applications. This is usual technology on the left, and on the right, photoalignment. So photoalignment technology can give you very high transmittance, high contrast ratio, high optical efficiency, and fast response time. And it has been demonstrated in 2009 in Japan plant. So here you will see the TV, which you can find in a shop in Hong Kong, with very high quality of color, resolution, and concentration. And then you can actually switch on light, and you can write and erase pictures on liquid crystal layer. We called it as a new type of Xerox, because in Xerox you can make Xerox only once, but here you can make 10,000 times. So the quality of the pictures is very good. You can have bright images on the dark background, or white images on the bright dark background, depending on the location of the polarizers. You can have two color images, changing, putting fluorescent dye opened, or changing for security applications. In comparison with other materials used for e-paper, electronic ink, our Azodyes are very high quality. You can write 3D image on our e-paper by subsequent writing for two images for your left and right eye, and put in lens array. And you can use it for different applications, for some labels, for ATM cards, for price labels, supermarkets, for sign and advertising, and so on. So as I told you, in comparison with electronic ink, you can have much better contrast ratio, cost effective, very high color triangle, high contrast ratio, and wide temperature. So according to this table, which we got from our collaborators in Nippon Ink and Chemicals, high quality paper can be much cheaper and much better than the cheapest liquid displays. And it is highly durable and flexible, lightweight, good brightness, high contrast ratio, wide viewing angle, low cost, no electrode, zero power consumption, and display units are separated. We are now working in full color paper and flexible substrates. So one of the applications is optically writable paper. Another application in field sequential display. So you know that liquid crystal displays are not green because of color filters and polarizers. So liquid crystal displays lose 95% of light. So in order to avoid filters, people use field sequential colors. So colors are put time sequentially, and your eye will integrate and have a color picture. So you use LED light for field sequential color. You can also use not 3 but 5 subframes, so you can use green, red, and green, blue. So 5 subframes, but you have very good improvement in power, but you must have very response time liquid crystals. And you also will have very high quality of color. So we start working in this direction in 1989 with Martin Schad, who is my friend and colleague. And we made ferroelectric liquid crystal cells based on photoalignment. Ferroelectric liquid crystal cells are shown here. And these ferroelectric liquid crystal are much faster than usual liquid crystal. They can get in a sub-microsecond time. So we have a lot of different electro-optical modes which are based on Azodye photoalignment technology. And this mode can have mechanical stability, have a high contrast ratio, can have a very fast response time. So we increase frequency for driving of liquid crystal to several kilohertz. And contrast ratio was more than 10 to 1. Color triangle was about 130%, and response time 15 microseconds, no problem. So we use pulse width modulation for making many colors, and we have no influence of neighbor pixels. So we have very high quality and high resolution displays, which has a very fast response time, small voltage, and wide color triangle, because we have many bits of gray level, and a very high quality of view. So here is a picture which will show you the field sequential color. We have about 16 millions of field sequential colors. We use different electro-optical modes to create displays, not only electrically suppressed helix, but different ferroelectric mode. And the key things in this mode is that we have very fast response time. And also we made for driving of liquid crystal, which are very fast. We cannot use usual TFT. We use IGZO TFT or low temperature polysilicon TFT, because response time of liquid crystal at least 10 or more times faster than usual crystal. So photoalignment will give you very high contrast ratio, fast response time, low power consumption, wide temperature range, and good color triangle and fast time. So in comparison with other liquid crystal, we can not only have fast response time, but we have this fast response time for very low voltage. So in principle, we can use special backplane like CMOS backplane, which is not allowed to use high voltage for the displays. And we have made so-called ferroelectric liquid crystal on silicon micro displays with very fast time and high resolution. We have been working with different companies who produce backplane like Hymax, AO, Varitronics, and so on. So the final product of us is different types of displays which can use for special application, for medical application, AR, VR, entertainment, and head-up displays, and definitely displays. We have demonstrated our devices in 2018 SID conference in Los Angeles, and we got these good results because we have very high resolution, low voltage, wide temperature range, response time. So we have 3 inches display. So, and here is myself, and here is my team. Here is my PhD students. Here is Professor Abhishek Srivastava, who continues this in HKUST. So, if ferroelectric liquid crystal made by photoalignment can be used also for virtual reality and augmented reality with high resolution and high quality. And these technologies are now coming to production. You can foresee many applications of these technologies, like optical network switch, LiDAR, 3D printing, engineering inspection, 3D face recognition, 3D fingerprint, spectral imaging, medical, and so on. So if you just summarize these applications, the market for FLC LCOS in China will be, only in China, will be more than 1 billion euros. Let's go to elements in display and photonics. In principle, by Azodye photoalignment, you can make a line liquid crystal monomer, and you can make face plates. You can make A plates, you can make O plates and C plates. You can also use these plates for 3D displays, because you can have different images for your left eye using these plates. Another very useful application is 100% polarizer. So if you write harmonic lattice of Azodye layer, you can have only two diffraction maximum. -1 is left-hand circular polarized light, and +1 is right-handed circular polarized. So you can have diffraction efficiency about 97%, not the diffraction, polarization efficiency, 97% if the angular divergence is less than 10 degrees. To make linear polarized light from circular polarized light, you can put on the top patterned plates. So you can improve considerably the efficiency of the backlight by 100% polarizer. In principle, you can make also retarders with very high efficiency. These pattern retarders will have efficiency. And also, you can make nanorods with quantum dots inside. You know that quantum dots, they can make very high color. But if you align them in nanorods, then you don't only have good color, but you will have very high efficiency, because the illumination will be in direction perpendicular to the nanorods. So degree of polarization can be very high in our photoalign nanodots with nanorods. We use for their alignment inkjet printing. So we change viscosity, surface tension, evaporation rate, and so on. And we have high quality results here. And very we can not only align, but we can pattern these nanorods, and then we can have very good quality later. We have very good without any polarizers, because we can align quantum dots, quantum rods. So we can considerably improve the efficiency of our alignment, and the efficiency can be used for improving the quality of liquid crystal alignment. Call me later, please. Okay, then let's more. We can have security films based on liquid crystal alignment. For security films, we can get security films observed only with one polarizer. We can change the brightness with rotation of the polarizers, and we can change the picture with rotation of the substrates. So here you will see what will be done in what you can do here. So you can get security films here with very high quality, and which seen only by polarizers. And if you can get it, you can rotate the polarizer, you can see different pictures of these security films. You can see here different pictures of security films. You can see after rotation of the polarizer, you can see different pictures of security films. Okay, the other application is smart windows. You know, the smart windows is windows which can change their transparency from opaque to transparent, or from transparent to opaque. We can use our, here is the table of comparison of our smart windows with liquid crystal smart windows, which is used for polymer dispersed liquid crystal. So we can see that our smart windows has much smaller voltage for changing. It is much more reliable and much more transparent than usual liquid crystal smart window. So here is the results of changing the transmittance from opaque to transmittance. Because we put our scattering structure not in the bulk but on the surface, our smart windows are much more reliable and stable than smart windows which use for polymer dispersed liquid crystal. There are several possibilities of scattering structures which can we use for our smart windows. Dependent on the location of liquid crystal parallel or perpendicular to the substrates, and dependent on the dielectric and isotropy of liquid crystals, you can change the structure from scattering to opaque, from opaque to transparent, or from transparent to opaque. Next application is liquid crystal photonics devices. Liquid crystal photonics devices, they are used to control the light in in fibers, and in principle you can control the light in using other devices, but are much better. I will tell you a little bit later about this. They can be used for liquid crystal waveguide interferometers, for beam steering, for tunable filters, tunable lasers, and these elements already in the market, like variable optical attenuators, polarization controllers, and phase shifters. And all parameters of these elements are comparable with usual liquid crystal which are used for this purpose. But one parameter is much better. This parameter is the power consumption, which is several orders of magnitude smaller than power consumption, which is used for usual elements using for changing the. For instance, if you like to change the intensity of the light of the fiber, you can change the refractive index of the cladding, and to change the refractive index of the cladding, you use liquid crystal element in the fiber. You can use also liquid crystal for optical data processing by writing Q plates. Q is a number here, so for different Q you will have different Q plates. They can be used in Fourier transformation to detect different objects with different frequencies. And these elements, liquid crystal elements, they can be very easily signed using digital mirror devices. And here is the pictures which were courtesied to me by my colleague, Professor Wai Hu. They are simple, high transmittance, broad wavelengths, tolerance from visible to terahertz, reconfigurable and reusable, flexible and new properties, and much higher damage. Also, you can use Photoaligned liquid crystal for beam steering. You just change the alignment of Photoaligned liquid crystal molecules, and you can change the direction of the light with very high diffraction efficiency. With very high diffraction efficiency, you can get the light efficiency. For instance, you change the angle by 4 degrees, you can have the diffraction efficiency more than 20%. You can also, in principle, use liquid crystal sensors. Liquid crystal sensors can be used, for instance, to visualize 4 Stokes parameters of the image. And to visualize 4 Stokes parameters of the image, you can detect not only the color and not only the color and not only the transmittance or reflectance, but you can actually detect the so-called invisible objects, for instance, bacteria in water, which has the same refractive. So, for instance, Stokes parameter S1 is the difference of the intensities between this and this subpixels, and Stokes parameters 2 is difference of intensities between this and this subpixels. You can put two CMOS image sensor, and you can simultaneously detect the whole picture. You can also use another sensor. You can use fiber break. You can use fiber with written break grating, and if you use reflected light from liquid crystal cell, you can measure electric field, you can measure sensor pressure, you can measure velocity. We have made this work together with my colleague at the University of New South Wales, and these sensors have been already done and has been made to measure the velocity, the pressure in pipelines and in minings, in like shown, but you just change the direction of liquid. When you change the direction of liquid crystal, you can change the focal of the lens. You can do it not only for non-polarized, for polarized light, but also non-polarized light. The voltage between 0 and you can also make liquid crystal display without polarizers if you can make effect here. If you make lens effect here, you can make liquid crystal display like this. So some scattering. If you have Fresnel, you can get an LED light, you can make full color picture on. You can also analyze objects using punch Banaramberi lens. You can simultaneously analyze right and left-handed polarized light, and you can do this for different applications: optical interconnect, spin photonics, optical, and so on. We have made this work together with my colleague in Taiwan University, and she made the glasses for people with different dioptries, and we can not only adjust dioptries for their eyes but also memorize. Another possibility for photoalignment in photonics is the liquid crystal micro-ring add drop filter. So the idea here is to change the resonance on the wall of the micro-ring and add and drop different in the fiber. By changing this, you can see that the picture is very complicated, very small. But we have made by photoalignment, we can make high quality pictures. We can change tunable range 20 nanometers. And finally, I would like to tell you that we can use photoalignment for reconfigurable antennas. So you know the antenna reconfigurability can be defined if you change frequency of antenna, pattern reconfiguration, and polarization configuration. So you make special configuration of antenna, you put liquid crystal by photoalignment and change impedance of antenna by changing the dielectric anisotropy of liquid crystal after application of the electric field. We can do this, we can change the frequency between 10 and 11 gigahertz, changing the antenna, and we are working now on 5G and 6G antennas. We can change not only an impedance of antenna, but we can also change the direction of radiation, because we can change the phase retardation between neighboring elements of antenna. So it can be new antennas with high transparency, reduced payload, reliable antennas, and can be operate in new liquid crystal materials with high dielectric anisotropy, high and multiple antennas to achieve beamforming of antennas. This is very promising technology. They can use not only on 4G, 5G, but even for terahertz 5G and 6G application. They can use in satellites, smart windows, and so on. So in summary, I would like to tell you that liquid crystal devices for displaying photonics are dominating in the market and will be the basic technology for advanced display and electronics in the nearest 10 years. Photoalignment materials can be effectively used in liquid crystal alignment and patterning for new generation of liquid crystal devices that provide extremely high resolution and optical quality of alignment, both in glass and plastic substrates. And now people should concentrate not only on displays, but they should make concentration on photonics application of liquid crystals like electronic paper, field sequential color displays like liquid crystal on silicon ferroelectric liquid crystal, photo pattern quantum rods and 100% polarizers, Q plates for optical data processing, sensors, switchable lenses, smart windows with voltage control transparency, security films, switchable antennas, and so on. Finally, I would like to attract your attention to my book, which has been published in 2014. I think now we should have a rewriting of this book. And this book is called Liquid Crystal Photonic. The aim of this book is to describe physical properties of liquid crystal, to show how to control liquid crystal behavior in electric field, to summarize basic electro-optical phenomena in liquid crystal, of definitely to introduce new photoalignment and photopatterning technology, and to show new photonics application of new photoaligned liquid crystal, like passive optical network systems, liquid crystal switches, polarization rotators, variable optical attenuators, and other photonics devices which can control the light, such as lenses, sensors, light converters, field sequential color LCDs, and so on. Finally, I am very happy that you attend my lecture.